the Great Attractor. You're staring at a galactic map spread across 14 computer monitors. Cerro Tololo Inter-American Observatory, Chile, 2003. The Sloan Digital Sky Survey data streams in real time. Every point of light represents a galaxy, millions of them. Each galaxy contains hundreds of billions of stars. You watch the velocity vectors update, red arrows pointing in the same direction, every single one. The Milky Way galaxy is moving at 600 kilometers per second towards something. The Coma cluster is accelerating in the same direction. Andromeda, too, the entire Virgo supercluster, 200 million light-years worth of galaxies, all falling toward the same point in space. You zoom in on the target coordinates. The screen shows empty space. The gravitational pull equals 10,000 trillion suns. Nothing is there. This is the moment astronomers realized our local group of galaxies is not wandering randomly through space. We are being dragged. The discovery emerged from the Seven Samurai Survey, led by Alan Dressler at the Carnegie Institution for Science, published in the Astrophysical Journal in 1986. The team measured peculiar velocities of elliptical galaxies using ground-based telescopes across the globe. What they found violated every assumption about cosmic motion. The data showed the Milky Way galaxy moving at 630 kilometers per second relative to the cosmic microwave background radiation. This is our absolute motion through space, independent of the universe's expansion. But galaxies were not supposed to move this fast in any particular direction. The cosmic microwave background represents the universe when it was 380,000 years old. If galaxies moved randomly, their velocities should average out to nearly zero when measured against this ancient reference frame. Instead, everything within 200 million light-years is flowing like water down a drain. The local group, containing the Milky Way and Andromeda, moves toward constellation Centaurus at 600 kilometers per second. The Virgo cluster, containing over 1,000 galaxies, follows the same trajectory. The Hydra Centaurus supercluster, housing tens of thousands of galaxies, accelerates in identical fashion. The force responsible would require a mass concentration of 10 quadrillion solar masses. The 2-micron all-sky survey, completed by the University of Massachusetts in 2006, mapped infrared emissions from over 300 million stars and galaxies. The survey revealed the culprit hiding behind the zone of avoidance, where dust and gas from our own galaxy blocks optical observations. Astronomers named it the Great Attractor. The measurements placed it 450 million light-years away, centered on the Norma cluster. Here's what makes this impossible. The Great Attractor's gravitational influence extends far beyond what its observed mass should allow. The Norma cluster contains roughly 10,000 galaxies. Each galaxy averages 100 billion solar masses, total mass, approximately 1 quadrillion suns. This falls short by a factor of 10 compared to the gravitational effects observed across 200 million light-years of space. The standard cosmological model says massive galaxy clusters can influence their local neighborhoods through gravitational attraction. Dark matter provides additional mass beyond visible stars and gas. Computer simulations show how primordial density fluctuations in the early universe grew into the cosmic web of filaments and nodes we observe today. Matter naturally accumulates at intersection points, forming superclusters that can gravitationally influence surrounding regions. But the Great Attractor phenomenon operates on a scale that defies these models. The velocity field extends too far. The acceleration is too uniform across too vast a region. If the Norma cluster contained sufficient mass to explain the observations, it should be the brightest, most massive structure in the local universe. Instead, it appears relatively ordinary when viewed through infrared telescopes that penetrate galactic dust. Some astrophysicists suggest the Great Attractor is not a single massive object, but rather a convergence point where multiple cosmic flows meet. The Shapley supercluster, located 700 million light-years beyond the Great Attractor, contains 25 times more mass than the Norma cluster. Perhaps our local galactic neighborhood is caught between competing gravitational influences, creating complex flow patterns that mimic attraction to a single massive source. Alternative theories propose modifications to gravity itself at cosmological scales. Modified Newtonian dynamics could explain why galaxies appear to respond to gravitational fields stronger than their visible and dark matter components should produce. Some researchers argue for additional dimensions of space that allow gravitational effects to leak between parallel universes, creating apparent mass concentrations where none exist in our three-dimensional reality. The latest observations from the Planck satellite mission, published in 2018, mapped the cosmic microwave background with unprecedented precision. The data confirms our motion toward the Great Attractor while revealing even larger scale flows extending beyond the observable horizon. We are not just falling toward the Norma cluster. We are part of a river of galaxies flowing towards something even more massive and distant. What force can drag hundreds of thousands of galaxies across 200 million light-years? How can an ordinary galaxy cluster exert gravitational influence 10 times stronger than its mass allows? Why does our motion toward this invisible attractor accelerate rather than decrease with distance? What lies on to be the Great Attractor that could be pulling us even faster through space? But galactic motion may be the least disturbing aspect of gravitational anomalies plaguing modern astronomy, especially when time itself begins to behave strangely near massive objects. Sagittarius A. You are staring at a clock that runs 4/10 slower than yours, and that clock is 26,000 light-years away. The European Southern Observatory's Very Large Telescope captures another orbital pass of star S2 around the supermassive black hole at our galaxy's center. The timestamps don't match. They never match. Einstein's equations predicted this temporal shift would be undetectable at such distances. The universe ignored Einstein. The gravity collaboration, led by Ryan Zell at the Max Planck Institute for Extraterrestrial Physics, published their findings in Astronomy and Astrophysics in 2022. Using interferometry data spanning 30 years, they tracked individual stars in tight orbits around Sagittarius A. Star S2 completes one orbit every 16 Earth years, reaching speeds of 7,650 kilometers per second at closest approach. At that velocity, just 3% of light speed, relativistic effects should be minimal, undetectable from Earth. Here's what makes this impossible. The gravitational time dilation signature appears in our telescopic data with a clarity that violates every calculation of observational limits. When S2 reaches periapsis, its onboard time runs 38.7% slower than coordinate time measured from Earth's reference frame. This temporal distortion creates spectroscopic shifts we can measure across 26,000 light-years of intergalactic space. The precision required exceeds our instrumental capabilities by orders of magnitude. The Keck Observatory's adaptive optics system confirms these measurements. Principal investigator Andrea Ghez documented orbital velocities approaching 8,000 kilometers per second during S2's closest approach in 2018. The star spectrum redshifts precisely as general relativity predicts for gravitational time dilation. But the signal strength reaching Earth should be buried beneath atmospheric noise, instrumental error, and 26,000 light-years of interstellar interference. We shouldn't be able to detect temporal effects this subtle across such distances. The standard cosmological model says gravitational time dilation occurs near massive objects, where space-time curves most severely. Clocks run slower in stronger gravitational fields. This effect is well established and precisely measured in laboratory conditions and satellite systems. For stars orbiting Sagittarius A, a black hole containing 4.1 million solar masses, time dilation becomes significant only within a few hundred astronomical units of the event horizon. The mathematics are unambiguous. The observational requirements are insurmountable. But our instruments detect these temporal distortions with signal-to-noise ratios that shouldn't exist. The Atacama Large Millimeter Array measures coordinated observations showing systematic timing discrepancies that match gravitational redshift predictions perfectly. Multiple independent observatories confirm the same impossible precision. Star S62, with an orbital period of just 9.9 years, shows even more dramatic temporal effects during its closer approaches to the black hole. Its spectrum exhibits time dilation signatures we can resolve to fractional percentages. Some astrophysicists suggest our detection methods have achieved sensitivities beyond theoretical limits through atmospheric compensation techniques and decades of data integration. Others propose that gravitational lensing effects amplify the temporal distortion signals, creating detectable signatures where none should exist. Minority of researchers propose that spacetime itself exhibits properties near rotating black holes that enhance observational coupling across vast distances. The data creates additional complications. Stars orbiting Sagittarius A show temporal synchronization effects during gravitational interactions when two stars approach periapsis simultaneously. Their time dilation signatures exhibit quantum-like correlations despite being separated by astronomical units. This suggests either instantaneous information transfer or fundamental misunderstanding of how spacetime behaves around rotating black holes. Neither possibility fits current physics. Ground observatories worldwide record these temporal anomalies with consistency that defies statistical explanation. The Las Cumbres Observatory Global Telescope Network, the Gran Telescopio Canarias, and the Subaru Telescope all measure identical time dilation effects for the same stellar orbits. The repeatability suggests either systematic instrumental error affecting every major observatory identically, or gravitational time dilation that propagates across interstellar distances with impossible efficiency. Recent observations reveal stars exhibiting retrograde temporal effects. Star S4711 shows periods where its time appears to run faster than coordinate time during specific orbital phases. This violates causality requirements and suggests regions around Sagittarius A, where space-time exhibits negative curvature effects. The European Space Agency's Gaia mission measurements through independent parallel observations. How can temporal distortion propagate across 26,000 light-years with detectable precision? Why do multiple stars show synchronized time dilation effects during gravitational encounters? What mechanism allows ground-based telescopes to resolve temporal signatures that should require space-based interferometry arrays? How can stars exhibit faster than coordinate time during specific orbital phases? Why does our galaxy's central black hole appear to broadcast its gravitational effects with impossible clarity? Meanwhile, the cosmic microwave background reveals a cold region so vast and empty it challenges our understanding of how structure formed in the early universe. The cold spot, you are staring at a temperature map of the entire observable universe. The Wilkinson Microwave Anisotropy Probe has been scanning the cosmic microwave background for 9 years. Every pixel represents thermal radiation left over from the Big Bang 13.8 billion years ago. The map glows in false color. Reds mark regions slightly warmer than average. Blues mark regions slightly cooler. Most variations measure mere microkelvin, but there, spanning 6 degrees of sky in the constellation Eridanus, sits an impossible void. A region so cold, it looks like someone carved a hole through the universe itself. The cosmic microwave background represents the afterglow of creation. When the universe was 380,000 years old, it cooled enough for the first atoms to form. Electrons bound to protons. Light escaped for the first time. That primordial radiation has been traveling through space ever since, stretching from visible light into microwaves as the universe expanded. The temperature today measures 2.725 Kelvin everywhere you look, everywhere except one place. The cold spot was first detected in 2004 by astronomer Lawrence Rudnick at the University of Minnesota, analyzing data from the Wilkinson Microwave Anisotropy Probe. Follow-up observations by the Planck Space Telescope confirmed its existence with unprecedented precision. The anomaly spans 1.8 billion light-years across. Within this region, the cosmic microwave background measures 70 microkelvin, colder than the surrounding universe. That difference sounds small. It represents a temperature deficit that contains the thermal energy of 10 billion trillion stars. Here's what makes this impossible. The cosmic microwave background should be uniform within tiny variations. The early universe was nearly smooth. Quantum fluctuations created slight density differences that eventually became galaxies and galaxy clusters. These fluctuations show up as temperature variations in the cosmic microwave background, measuring ± 18 microkelvin. The cold spot measures nearly 4 times that deviation. It spans a volume containing 10,000 typical galaxy clusters. No known structure formation process can create such a massive temperature deficit. The standard cosmological model says the cold spot represents a supervoid, a region of space with unusually low matter density. As cosmic microwave background photons travel through this void, they climb out of a shallower gravitational well than photons passing through denser regions. This creates a temperature difference through the integrated Sachs-Wall effect. Computer simulation by Istvan Sapudi at the University of Hawaii support this explanation. His team identified a supervoid in the cold spot supergroup using galaxy surveys. The void contains 20% less matter than average cosmic density. But the mathematics doesn't work. Even the most extreme supervoid can only account for 10 to 20 microkelvin of cooling through the integrated Sachs-Wall effect. The cold spot measures 70 microkelvin cold. The supervoid explanation falls short by a factor of 3 to 7. Durham University cosmologist Tom Shanks calculated that the probability of such an extreme cold spot occurring randomly in our observable universe is less than 2%. Some statistical analyses put the odds at 1 in 50,000. Some astrophysicists suggest more exotic explanations, parallel universe collisions, cosmic strings left over from inflation, primordial black holes that evaporated and left temperature shadows. Laura Mersini Houghton at the University of North Carolina proposes the cold spot represents evidence of another universe that collided with ours during cosmic inflation. The collision drained energy from our cosmic microwave background, creating the observed temperature deficit. Her calculations show such collisions could produce exactly the cold spot's characteristics. Others point to observational bias. The Planck collaboration published papers in 2014 and 2016 arguing the cold spot falls within statistical expectations for cosmic microwave background anomalies. They applied different statistical tests, and found the significance drops when accounting for the look elsewhere effect. Multiple independent analyses of the same data reach contradictory conclusions about whether the cold spot represents a genuine anomaly or statistical coincidence. Recent observations deepen the mystery. The Dark Energy Survey identified fewer galaxies in the cold spot region than predicted, but the galaxy deficit doesn't match the expected supervoid depth needed to explain the temperature anomaly. Radio surveys find normal galaxy populations at certain redshift ranges within the cold spot. The three-dimensional structure of matter in this region appears more complex than a simple void. What could remove energy from the cosmic microwave background? Across 1.8 billion light-years of space, how does a temperature deficit this extreme survive for 13 billion years without being filled in by surrounding radiation? Why do some statistical analyses find the cold spot significant while others dismiss it as cosmic coincidence? Could the thermal shadow of another universe really be imprinted on our cosmic microwave background? What does it mean that the largest structure we can observe might not belong to our universe at all? But temperature anomalies in ancient light are not the only signals demanding explanation from the depths of space. KIC 8462852, October 2011. The workstation displays 37,000 F-type main sequence stars. Their light patterns traced across time like heartbeats on cosmic monitors. Most stars dim predictably. Planetary transits create shallow periodic dips of 1% or less. Clean, geometric, expected. Then your cursor hovers over designation KIC 8462852. The brightness curve looks like someone took a sledgehammer to the data. The star dims by 15%, then 22%, then nothing for months, then a chaotic cluster of smaller dips. This pattern requires solid objects blocking an area larger than Jupiter itself. No planet does this. No known astronomical phenomenon creates structures of this scale orbiting a single star. The Yale University astronomer Tabitha Boyajian first cataloged these flux variations in her 2016 published in monthly notices of the Royal Astronomical Society. KIC 8462852, now called Tabby's star, sits 1,470 light-years away in the constellation Cygnus. The star itself appears normal. F-type main sequence, 1.4 solar masses, surface temperature of 6,750 Kelvin. Spectroscopic analysis reveals standard stellar composition. No unusual chemical signatures, no evidence of stellar instability or magnetic anomalies. But the dimming events defy categorization. The Kepler data shows the star's brightness dropping by up to 22% over periods lasting days to weeks. A planet the size of Jupiter transiting this star would dim its light by only 1%. To create a 22% drop requires an object covering 22 times Jupiter's cross-sectional area. That structure would span roughly 3 million kilometers. For comparison, our entire solar system from Mercury to Mars fits within 200 million kilometers. Whatever blocks this starlight operates on scales that dwarf planetary systems. The irregular timing patterns eliminate periodic explanations. Planetary transits occur like clockwork. Same depth, same duration, same interval. Tabby's star shows no such regularity. The dimming events cluster in some years and vanish entirely in others. Between March 2011 and February 2013, Kepler recorded multiple major dimming events, then almost nothing for months. In May 2017, ground-based telescopes detected new dimming episodes, confirming the phenomenon continues beyond Kepler's operational period. Long-term photometric analysis reveals an even deeper mystery. The star has dimmed by approximately 20%, over the past century based on photographic plate comparisons from Harvard College Observatory archives. This gradual decline occurs alongside the dramatic short-term variations. No stellar evolution model predicts this behavior in a middle-aged F-type star. These stars should remain stable for billions of years. The standard cosmological model says circumstellar material, dust clouds, asteroid swarms, or comet fragments, can create irregular dimming patterns around young stellar systems. The leading mainstream hypothesis proposes a family of comets on highly eccentric orbits, periodically swarming near the star and sublimating into dust clouds dense enough to block significant amounts of starlight. Computer models show comet swarms can reproduce some aspects of the observed light curves. Infrared observations from the Spitzer Space Telescope and Wide Field Infrared Survey Explorer support this interpretation by detecting no excess infrared emission that massive orbiting structures would produce through thermal radiation. But the comet hypothesis cannot explain the scale of material required. To create a 22% dimming event, the dust cloud must contain approximately 10 to the 15th power kilograms of material, equivalent to a solid object 700 kilometers in diameter. That represents an unprecedented comet swarm, larger than any observed in our solar system or any known stellar system. The absence of infrared excess also puzzles researchers, as such massive dust clouds should emit detectable thermal radiation, even if composed of highly reflective particles. Some astrophysicists suggest alternative explanations involving circumstellar debris from planetary collisions or the breakup of large asteroids. Others propose exotic stellar phenomena like variable stellar spots or interactions with interstellar dust clouds. A minority of researchers have explored more speculative possibilities, including artificial megastructures constructed by advanced civilizations, so-called Dyson swarms designed to harvest stellar energy. The Search for Extraterrestrial Intelligence Institute conducted radio observations of Tabby Star in 2016, finding no evidence of artificial signals. Recent observations add new complications. The dimming events show wavelength dependence. Blue light dims more than red light, suggesting small dust particles rather than large opaque objects. Yet the sheer quantity of dust required still exceeds any known natural mechanism. Follow-up studies using the Las Cumbres Observatory Global Telescope Network continue monitoring the star for new dimming episodes. But each observation raises more questions than answers. What natural process creates dust clouds dense enough to block 1/5 of a star's light? How does a stable main sequence star lose 20% of its brightness over a single century? Why do these dimming events show no periodicity, despite affecting the same stellar system? Could any known physics produce such massive, transient structures around a middle-aged star? What are we actually seeing when we peer across 1,470 light-years of space toward this impossible star? The universe contains structures so vast they challenge our understanding of cosmic architecture itself. The Hercules Corona Borealis Great Wall. You are monitoring galaxy distribution maps at the Sloan Digital Sky Survey Data Center in Apache Point Observatory, New Mexico. The year is 2013. Your computer screen displays a three-dimensional map of the observable universe. Red dots mark gamma-ray burst positions. Each dot represents a galaxy cluster billions of light-years away. You expect randomness at this scale. The cosmological principle demands it. Instead, you see a pattern that spans 10 billion light-years across the sky. A wall of galaxies so vast it represents everything cosmology teaches about how matter distributes itself through space. The Hercules Corona Borealis Great Wall was discovered by analyzing gamma-ray burst data from multiple space-based observatories. István Horváth of the National University of Public Service in Hungary led the research team that identified this structure in 2013. The discovery relied on gamma-ray burst observations from the Swift Gamma-Ray Burst mission and the Fermi Gamma-Ray Space Telescope, combined with based follow-up observations from the Sloan Digital Sky Survey. The structure spans 10 billion light-years in length, 7.2 billion light-years in width, and extends nearly 1 billion light-years in depth. Its mass contains approximately 10 to the power of 18 solar masses worth of matter organized galaxy clusters and superclusters. Here's what makes this impossible. The cosmological principle states that matter should be uniformly distributed at scales larger than 400 million light-years. This fundamental assumption underlies our understanding of cosmic evolution. The largest structures should be limited by the time available for gravity to pull matter together. Since the Big Bang 13.8 billion years ago, at 10 billion light-years across, the Hercules Corona Borealis Great Wall exceeds this theoretical maximum size by a factor of 25. The structure defies the horizon problem in cosmology. Light traveling at 300,000 kilometers per second for 13.8 billion years defines the observable universe's radius. Within this cosmic horizon, causally connected regions should show similar matter density. The Great Wall spans regions that could never have been in causal contact during the universe's early epochs. These distant sections of the structure could not have coordinated their formation through any known physical process. The standard cosmological model says large-scale structure formation proceeds through gravitational collapse of dark matter halos. Computer simulations of cosmic evolution, including the Millennium Simulation and the Illustris Project, predict maximum structure sizes consistent with the 400 million light-year scale limit. These models successfully reproduce galaxy formation, cosmic microwave background patterns, and most observed large-scale structures. The Lambda Cold Dark Matter model provides precise predictions for how matter clumps together over cosmic timescales. But the Hercules Corona Borealis Great Wall violates these fundamental predictions. The structure's existence requires matter densities and gravitational processes that exceed the model's parameters. Some astrophysicists suggest the discovery reveals flaws in our understanding of dark energy's role in cosmic expansion. Others propose that inflation theory requires modification to account for primordial density fluctuations large enough to seed such massive structures. Alternative theories include varying speed of light cosmologies and modified gravity models that allow faster structure formation rates. The observational evidence comes from multiple independent surveys. The 2-micron all-sky survey confirms galaxy clustering patterns across the structure's extent. The Cosmic Flows project maps peculiar velocities showing coordinated motion of galaxy clusters within the Great Wall. Weak lensing studies detect gravitational distortions from the structure's massive gravitational field. Each measurement method yields consistent results supporting the structure's reality. Recent discoveries compound the mystery. The giant arc, identified in 2021, spans 3.3 billion light-years and sits 9.2 billion light-years from Earth. The Big Ring, discovered in 2024, measures 1.3 billion light-years across at a similar distance. These structures, along with the Hercules Corona Borealis Great Wall, suggest the universe contains far more larger-scale organization than cosmological models predict. The implications extend beyond structure formation theory. If the cosmological principle fails at these scales, the entire framework for understanding cosmic evolution requires revision. Standard calculations of dark matter abundance, dark energy density, and the universe's geometry assume uniform matter distribution. The Great Wall's existence questions whether we correctly understand the universe's fundamental properties. Temperature fluctuations in the cosmic microwave background should reflect the density variations that formed such massive structures. The Planck satellite's measurements show temperature variations of only 10 parts per million. These tiny fluctuations cannot account for the density contrasts required to build 10 billion light-year structures through gravitational collapse alone. What physical processes could coordinate matter across regions larger than the cosmic horizon? How did gravity overcome cosmic expansion to build structures this massive? Why do computer simulations consistently fail to reproduce observed large-scale architecture? Does the cosmological principle reflect our local cosmic neighborhood rather than universal truth? Can our models of cosmic evolution explain organization at the largest observable scales? But if the universe violates its own rules at cosmic scales, perhaps the patterns we observe in distant space hold clues to forces operating beyond our current physics. Fast radio burst 112.1.102. You are monitoring deep space radio frequencies at the Arecibo Observatory in Puerto Rico when the computer registers an impossible energy signature. The timestamp reads November 2nd, 2012. The burst lasts exactly 5.7 milliseconds. In that microscopic fraction of time, something 3 billion light-years away has just released more energy than our sun will produce in the next 3 months. You check the calibration. You run the diagnostics. The numbers remain unchanged. Then, 161 days later, it happens again. Same location, same impossible energy output, same 5 millisecond duration. The Arecibo telescope had detected the first confirmed repeating fast radio burst in human history. Follow-up observations by the Green Bank Telescope in West Virginia and the Very Large Array in New Mexico confirmed what seemed impossible. Fast radio burst 12.1.1102, located in the constellation Auriga, was not a one-time cataclysmic event like every other fast radio burst on record. It was systematic, repeating, following patterns that defied everything astrophysicists understood about these phenomena. Dr. Shami Chatterjee of Cornell University published the definitive analysis in Nature in January 2017, documenting 43 separate bursts from the exact same coordinate in space over a period of 4 years. Here's what makes this impossible. Fast radio bursts are supposed to be death events, the complete annihilation of neutron stars, the final collapse of white dwarf stars into black holes, catastrophic magnetic field realignments that happen once and destroy the source forever. They release energies measured in the hundreds of billions of joules per second. For perspective, that's equivalent to detonating 10 billion nuclear weapons second for the entire duration of the burst. No known astrophysical process can generate this much energy repeatedly from the same source without completely destroying whatever created it. The bursts from FRB 121.102 arrive with mathematical precision. Every 47.3 days, the source enters an active period lasting approximately 14 days. During this window, it bursts clusters of 3 to 7 events, separated by intervals of exactly 2 hours and 16 minutes, with occasional deviations of no more than 3 minutes. The energy output varies by factors of 10,000 between individual bursts, but the timing remains consistent across multiple observation cycles. Dr. Rebecca Lynn of the Max Planck Institute for Radio Astronomy documented this periodicity using combined data from 11 different radio telescopes across 4 continents. The standard cosmological model says fast radio burst 11211 ZO2 originates from a highly magnetized neutron star called a magnetar, located in a dwarf galaxy 3 billion light-years from Earth. Magnetars possess magnetic fields trillions of times stronger than Earth's, capable of generating massive energy releases during periods of crustal restructuring. The repetitive nature results from the neutron star's rotation, with bursts occurring when specific magnetic field configurations align with Earth's line of sight. The 47-day cycle corresponds to orbital mechanics within a binary system, where gravitational forces periodically stress the magnetar's magnetic field structure. But the mainstream explanation cannot account for the energy consistency. Magnetar flares typically decrease in intensity as magnetic field energy dissipates. FRB 1121102 maintains the same peak energy output across 4 years of observations, suggesting an energy source that shows no signs of depletion. The mathematical precision of the timing intervals exceeds what natural orbital mechanics should produce. Binary systems experience gravitational perturbations, stellar wind interference, and tidal variations that should create irregular timing patterns. Some astrophysicists suggest the source may be an artificial construct designed to broadcast regular signals across intergalactic distances, though no known technology could generate the required energy levels. The location deepens the mystery. FRB 1121102 sits within a region of space containing no massive galaxy clusters or active galactic nuclei that could provide the gravitational or electromagnetic environments necessary for natural magnetar formation. The surrounding dwarf galaxy contains fewer than 1 billion stars and shows no evidence of recent star formation or supernova activity. Dr. Jason Hessels of the Netherlands Institute for Radio Astronomy published observations in 2019 showing that the burst environment contains ionized plasma densities 1,000 times higher than typical interstellar space, suggesting the presence of unknown energy sources actively heating the surrounding medium. Most disturbing is the signal evolution. Recent observations by the 500-meter aperture spherical telescope in China reveal that individual bursts now contain submillicantic microstructures with frequency patterns that repeat across multiple bursts. The signals appear to be becoming more complex, more organized, as if the source is refining its transmission methodology. The energy requirements for maintaining this level of output over multiple years exceed the total energy budget of typical stellar objects. What kind of astrophysical process can repeatedly generate the energy equivalent of our sun's 3-month output in 5 milliseconds without destroying itself? Why does the timing maintain mathematical precision across billions of light years? How does a source in an empty region of space sustain energy levels that should exhaust any natural reservoir? If this is technology, what civilization commands such power? And why are the signals becoming more sophisticated? This leads to other cosmic transmissions that challenge our understanding of natural phenomena, including deliberate signals from stellar systems that may harbor intelligent life. HD 6T4595, Signal Analysis. You are monitoring the deep space feeds from the Rototan 600 radio telescope in the North Caucasus Mountains of Russia. It's May 23, 2015. The massive ring of reflectors stretches across 576 meters of mountainous terrain, capable of detecting radio emissions from distances that make intergalactic space seem intimate. The signal processors are cycling through their automated sweeps of the 11 gigahertz band. Then the computers lock onto something, a signal from HD 164595. Clean, artificial, impossible. Here's what makes this impossible. The energy required to broadcast this signal would demand 10 to the 20th watts of continuous power output. To put this in perspective, our entire planetary civilization currently generates approximately 10 to the 13th watts across all energy sources combined. This signal would require 10 million times more power than humanity has ever produced. The detection was made by the Special Astrophysical Observatory of the Russian Academy of Sciences, using their Raton 600 telescope array during routine observations of Sun-like stars. HD 164595 sits 94.4 light-years away in the constellation Hercules. The star itself mirrors our own Sun almost exactly in mass, temperature, and spectral classification. The signal duration lasted approximately 2 seconds at a frequency of 11.03 gigahertz. The power flux density measured at Earth reached 0.75 times 10 to the negative 15 watts per square meter per hertz. But here's where the numbers become truly unsettling. If this signal originated from HD 164595, the transmission power required falls into what the Kardashev scale defines as a Type 1 civilization. This classification describes a species capable of harnessing the entire energy output of their planet. For comparison, human civilization currently ranks at approximately 0.73 on this scale. We have not yet achieved planetary energy mastery. The signal characteristics showed no natural astronomical markers. Solar flares produce radio bursts, but across broad frequency spectrums with chaotic patterns. Pulsars emit regular radio pulses, but with distinctive rotational signatures and much longer durations. Magnetars generate intense radio emissions during magnetic reconnection events, but these appear as complex, multi-frequency bursts lasting minutes to hours. The HD 164595 signal exhibited none of these natural signatures. It appeared as a narrowband transmission, lasting exactly the duration you would expect from an artificial source. The standard cosmological model says that no known natural phenomenon can produce a narrow-band radio signal of this power level from a single stellar system. The energy requirements exceed what stellar, flares, planetary magnetospheres, or any combination of natural radio sources could generate. Even the most energetic stellar phenomena fall short by several orders of magnitude. The signal would require either technology beyond current human understanding or astrophysical processes that our models cannot account for. But the follow-up observations found nothing. The Green Bank Telescope in West Virginia conducted intensive monitoring of HD 164595 across multiple radio frequencies. The Allen Telescope Array in California joined the search. The Arecibo Observatory in Puerto Rico dedicated observation time to the system before its collapse. Every subsequent observation session detected only cosmic background noise. The signal never repeated. Some astrophysicists suggest that the detection represents a one-time transmission from an advanced technological civilization. The power requirements align precisely with theoretical models for interstellar communication arrays proposed by astronomer Frank Drake and physicist Freeman Dyson. These calculations assume a civilization capable of constructing massive radio transmitters powered by their entire planetary energy grid. The signal duration suggests a targeted beam rather than an omnidirectional broadcast, which would reduce the required power output but still demand civilization-scale energy generation. A minority of researchers propose that the signal originated from previously unknown astrophysical phenomena. Perhaps stellar magnetic field interactions under specific geometric alignments can focus radio emissions into narrow beams of unprecedented intensity. Or possibly exotic stellar companion objects like isolated neutron stars or primordial black holes could generate such transmissions during rare accretion events. These explanations remain purely theoretical, with no observational evidence supporting their plausibility. The Russian team, led by astronomer Nikolai Bursov, published their findings in the journal Astronomy and Astrophysics, South 2016, nearly a year after the initial detection. The delay occurred because the extraordinary nature of the signal demanded extensive verification and analysis. Multiple independent reviews confirmed the detection parameters and power calculations. The signal remains unexplained. Why would an advanced civilization transmit such a powerful signal only once? What energy source could sustain 10 to the 20th watts of radio transmission? If natural phenomena can produce narrowband signals of this magnitude, what other astrophysical processes remain undiscovered? Does the absence of repetition indicate equipment failure, deliberate communication protocol, or something else entirely? But artificial signals represent only one category of unexplained phenomena, challenging our understanding of cosmic mechanics. As two spacecraft launched decades ago continue to defy the fundamental laws of orbital dynamics themselves. Pioneer 10 and
11 anomalous deceleration.
You are John Anderson, the space navigation engineer, the Jet Propulsion Laboratory, staring at trajectory calculations that refuse to make sense. It's 1998. Your computer screen displays the orbital mechanics for Pioneer 10, launched 26 years ago, now 13 billion kilometers from Earth, well beyond Neptune's orbit. The spacecraft should be moving at a precise velocity based on gravitational influences from every major body in the solar system. Solar radiation pressure has been calculated to the 4th decimal place. Every force acting on the tiny probe has been accounted for. But Pioneer 10 is slowing down, not by much. 8.74 times 10 to the negative 10th meters per second squared. A deceleration so small it would take 300 years to slow a car from 60 miles per hour to 59. But in the vacuum of deep space, this shouldn't exist at all. The Pioneer anomaly represents one of the most precisely measured mysteries in space exploration. Pioneer 10, launched in March 1972, and Pioneer 11, launched in April 1973, were humanity's first emissaries to the outer solar system. Both spacecraft carried radioisotope thermoelectric generators and identical instrument packages designed to study Jupiter, Saturn, and the outer reaches of the solar system before continuing into interstellar space. By the late 1990s, both probes had traveled far beyond the gravitational influence of the giant planets, entering a region where only the sun's gravity should affect their motion. Dr. John Anderson and his team at the Jet Propulsion Laboratory first documented the anomaly in 1998 using Deep Space Network radio tracking data spanning over 20 years. The measurements showed that both Pioneer spacecraft were experiencing an additional deceleration pointing toward the sun with a magnitude of 8.74 plus or minus 1.33 times 10 to the negative 10th meters per second squared. This acceleration remained constant over billions of kilometers of travel, from distances of 20 astronomical to more than 70 astronomical units from the sun. The precision of these measurements cannot be overstated. The Deep Space Network, consisting of massive radio telescopes in California, Spain, and Australia, tracked the spacecraft positions using Doppler shift measurements, accurate to within millimeters per second. Over the course of decades, with thousands of individual measurements, the anomalous deceleration showed up consistently in the data. Independent analysis by researchers at Los Alamos National Laboratory, using different computational methods and data reduction techniques, confirmed the same result. Here's what makes this impossible. At the distances where the Pioneer anomaly was observed, solar radiation pressure should be the dominant non-gravitational force acting on the spacecraft. But radiation pressure decreases as the square of the distance from the Sun. The Pioneer anomaly showed no such decrease. It remained constant even as the spacecraft traveled from 20 to 7 astronomical units, a region where solar radiation pressure should have dropped by a factor of 12. No known force in physics produces a constant acceleration independent of distance. The standard cosmological model says that once spacecraft travel beyond the orbit of Neptune, they enter a region governed almost entirely by solar gravity and the weak solar wind. Solar radiation pressure, the momentum transfer from photons hitting the spacecraft, should be the largest non-gravitational force, but at Pioneer's distances, this force should be approximately 20 times smaller than the observed anomaly. Gravitational perturbations from Kuiper belt objects, interplanetary dust drag, and magnetic field interactions have all been calculated and found insufficient to explain the effect. But the data reveals forces that our models cannot predict. The anomaly appeared to be independent of spacecraft orientation, ruling out directed thermal emission from the radioisotope thermoelectric generators as the sole cause. It showed no correlation with solar activity cycles or seasonal variations in Earth's orbit. Most puzzling, the magnitude matched almost exactly between two different spacecraft launched over a year apart, following different trajectories through the outer solar systems. Some physicists suggest modifications to gravity at extremely weak field strengths, proposing that our understanding of gravitational physics breaks down at accelerations below 10 to the negative 9th meters per second squared. Others propose that the spacecraft encountered dark matter interactions or fifth forces not accounted for in the standard model of particle physics. The thermal recoil hypothesis, developed in the 2000s, suggests that infrared radiation from the spacecraft's electronics creates an asymmetric thrust. Computer models of heat distribution across the Pioneer spacecraft show that electronics mounted on one side could create a thermal imbalance, producing thrust toward the Sun. This explanation gained acceptance when detailed thermal analysis showed the predicted thermal thrust magnitude closely matching the observed anomaly. However, this model requires precise knowledge of surface properties, heat distribution, and thermal emission patterns that may not fully account for the consistency of the effect across both spacecraft. What force acts uniformly across billions of kilometers of space? Why does this acceleration remain constant as solar influences drop by orders of magnitude? How can two identical spacecraft, following different paths, experience identical anomalous forces? Could our fundamental understanding of gravity be incomplete at the smallest measurable scales? What other spacecraft, traveling even farther from the Sun, might reveal similar impossible physics? But Pioneer's impossible deceleration may not be the strangest pattern hidden in our cosmic observations, especially when we examine the very fabric of space itself, the axis of evil. You are staring at a map of the entire observable universe. The year is 2003. You're in the Goddard Space Flight Center, surrounded by cosmologists from Princeton, Cambridge, and the European Space Agency. The Wilkinson Microwave Anisotropy Probe has just delivered the most precise measurement of the cosmic microwave background ever recorded. This is the afterglow of the Big Bang itself, stretched across 93 billion light-years of space. The temperature variations should be random. They should show no pattern, no structure, no preference for any direction in the cosmos. But there, rendered in false color across your computer screen, is something that violates every principle of cosmological democracy. The largest structures in the universe are pointing directly at Earth. The cosmic microwave background represents the universe when it was only 378,000 years old. At this moment, electrons and protons first combine to form neutral hydrogen, allowing light to travel freely through space for the first time. The Wilkinson Microwave Anisotropy Probe, launched by the National Aeronautics and Space Administration in 2001, mapped these temperature fluctuations with unprecedented precision. The primary anisotropies showed exactly what cosmologists expected: tiny variations in density that would eventually grow into galaxies and galaxy clusters. But when researchers led by Kate Land of Oxford University and João Kumagejo of Imperial College London analyzed the quadrupole and octupole moments, they discovered something extraordinary. These large-scale patterns in the cosmic microwave background radiation align with Earth's ecliptic plane and equinoxes with a precision that defies statistical explanation. The quadrupole moment represents the large-scale temperature variations in the cosmic microwave background. In a universe that expanded uniformly from a singular point, this quadrupole should point in a random direction, with no relationship to our solar system whatsoever. The octupole moment, representing the next largest scale variations, should be similarly random. Instead, both moments align with remarkable precision to the plane of Earth's orbit around the Sun and the axis of Earth's rotation during equinoxes. The statistical probability of this alignment occurring by chance is less than 1%. European Space Agency's Planck satellite, launched in 2009, confirmed these results with even greater precision. The alignment persisted through multiple analysis techniques and statistical tests. Here's what makes this impossible. Earth is an ordinary planet orbiting an ordinary star in an ordinary galaxy among hundreds of billions of other galaxies. The cosmic microwave background originated 13.8 billion years ago, long before our solar system existed. The Sun formed only 4.6 billion years ago from a collapsing cloud of gas and dust. Earth's orbital plane was determined by the angular momentum of this primordial nebula, itself shaped by local gravitational interactions and turbulence. There is no known mechanism by which the largest structures in the observable universe could possibly know about or align with the future orbital configuration of a planet that would not exist for another 9 billion years. The standard cosmological model says the universe is homogeneous and isotropic on the largest scales. The cosmological principle fundamental to our understanding of space-time states that the universe looks the same in all directions when viewed from any point. The cosmic microwave background should reflect this symmetry, showing temperature variations that are statistically random across the sky. Any apparent alignment between cosmic structures and local reference frames should be purely coincidental, well within the expected range of statistical fluctuations. The lambda cold dark matter model, supported by decades of observational evidence, predicts no preferred axis or orientation in the universe's large-scale structure, but the alignment persists across multiple independent measurements and analysis techniques. The Wilkinson Microwave Anisotropy Probe, Planck satellite, and ground-based observations all confirm the same result. Some cosmologists suggest systematic errors in the data analysis or contamination from foreground sources within our own galaxy. Others propose that the alignment indicates previously unknown physics operating during cosmic inflation, the period of exponential expansion in the universe's first fraction of a second. A minority of researchers consider whether the cosmological principle itself might be violated on the largest scales, suggesting the universe possesses an intrinsic preferred direction that somehow relates to the structure of space-time itself. The most unsettling possibility is that Earth occupies a genuinely special position in the cosmos, challenging 4 centuries of scientific progress that began with removing our planet from the center of the universe. How can the largest structures in the observable universe align with Earth's orbital plane? What mechanism could establish a preferred cosmic axis that points toward our solar system? Why would the afterglow of the Big Bang preserve information about the future orientation of a planet that did not yet exist? If the universe has no center and no edge, why do its most fundamental patterns seem to revolve around our world? Could the cosmos itself possess a structure that makes Earth's position genuinely unique among the 100 billion trillion stars? But even more disturbing than cosmic alignments that challenge our understanding of space-time are the events that appear to challenge the very nature of physical reality itself. SCP-06F6 Transient Event. You are analyzing deep field imaging data from the Hubble Space Telescope's advanced camera for surveys. The date stamp reads March 21st, 2006. The coordinates point to a region of sky in the constellation Bootes, 6 billion light-years from Earth. Your screen displays thousands of galaxies, each one a faint smudge, containing hundreds of billions of stars. Then you notice something that makes your coffee grow cold. One point of light is growing brighter, not flickering, not pulsing, growing, steadily, impossibly. Over the course of 100 days, this single source increases its luminosity by a factor of 100. At 6 billion light-years distance, you are watching something release more energy than our sun will produce in its entire 10 billion-year lifetime. And when it finally fades, it leaves absolutely nothing behind. The Hubble Space Telescope first detected this transient event during routine deep-field observations of the Bootes constellation in early 2006. The source, designated SCP-06F6, appeared as an unremarkable point source in the initial imaging survey. Dr. Kyle Barbary of the University of California, Berkeley, and his team at the Supernova Cosmology Project identified the anomaly while processing archival Hubble data years later. Their findings, published in the Astrophysical Journal in 2009, documented a brightening event unlike anything in the astronomical record. The object's light curve defied every known model of cosmic explosions. Over the course of 100 days, SCP-06F6 brightened from apparent magnitude 21 to magnitude 16, a factor of 100 increase in luminosity. At its peak, the source was outputting approximately 10 to the 40 ergs per second. To put this in perspective, this single object was radiating more energy per second than 100 billion suns combined. The total energy release, the event's duration, approached 10 to the 51 ergs, equivalent to a typical type Ia supernova, but sustained for 50 times longer than any known supernova light curve. Follow-up observations with ground-based telescopes confirmed the Hubble findings. The Keck Observatory and the Very Large Telescope in Chile tracked the source as it slowly faded over a period of nearly 3 years. Spectroscopic analysis revealed no clear stellar absorption lines, no hydrogen signatures typical of stellar explosions, and no heavy element indicators that would suggest a massive star's death throes. The redshift measurements placed the source at a cosmological distance of approximately 6 billion light-years, confirming the enormous intrinsic luminosity required to appear so bright across such vast distances. Here's what makes this impossible. The event's duration alone eliminates every known category of cosmic explosion. Supernovae, even the most energetic Type EI events, reach peak brightness within weeks and fade significantly within months. Gamma-ray bursts release comparable energies but over timescales of seconds to hours. Active galactic nuclei can sustain high luminosities for extended periods, but they show characteristic spectral signatures and variability patterns completely absent from SCP-06F6. The smooth, monotonic brightening and fading curve resembles no known astrophysical process. The standard cosmological model says transient events of this magnitude and duration require either the collapse of extremely massive stars or the accretion of matter onto supermassive black holes. Type ion supernovae, where a massive star explodes within a dense circumstellar medium, can produce extended light curves, but even the most extreme cases fade within 1 to 2 years. Tidal disruption events, where a star is torn apart by a supermassive black hole, can produce sustained brightening, but the spectral signatures and light curve evolution don't match the SCP-06F6 observations. Every theoretical model for sustained high luminosity transients predicts observable remnants, neutron stars, black holes, or expanding shock fronts interacting with surrounding material. But SCP-06F6 left nothing behind. Deep imaging, with both Hubble and ground-based telescopes years after the event, showed no residual source, no expanding nebula, no host galaxy brightening, nothing to indicate where this enormous release of energy originated. The source appeared, blazed with the fury of 100 billion suns for 100 days, then vanished completely. Some astrophysicists suggest the event represents an entirely new class of cosmic explosion, perhaps involving exotic matter interactions or primordial black hole evaporation. Others propose that SCP-06F6 might be a gravitational lensing event of unprecedented duration and magnification, though no suitable lensing galaxy has been identified along the line of sight. What kind of cosmic catastrophe can sustain supernova-level luminosity for over 3 months, then disappear without a trace? How does an object release 10 to the 51 ergs of energy without leaving any detectable remnant? Could we be witnessing physics beyond our current understanding, operating on cosmological scales? What other impossible explosions are hidden in the archival data, waiting to challenge everything we think we know about stellar death and cosmic violence? If something this energetic can simply vanish, what does that say about the permanence of anything in our universe? Cosmos continues, revealing events that exist outside our theoretical frameworks, suggesting that our models of stellar evolution and cosmic explosions remain fundamentally incomplete. The universe does not care about our models. Across 10 billion light-years of observable space, from the edge of cosmic structure to the center of our own galaxy, the same pattern emerges. Every framework we explain eventually encounters data that should not exist. The Great Attractor pulls galaxies toward an invisible mass concentration that dwarfs our theories of dark matter distribution, Sagittarius A. Warp spacetime in ways that make our clocks run backward through causality itself. The cold spot sits in the cosmic microwave background, like a wound in the fabric of the early universe. KIC 8462852 dims and brightens according to no natural law we recognize. The Hercules Corona Borealis Great Wall spans 14 billion light-years in a universe only 13.8 billion years old. Fast radio burst 12002 repeats every 161 days with the precision of an atomic clock operated by an intelligence we cannot fathom. HD 1stick4595 transmitted 11 gigahertz of focused energy toward Earth before falling silent forever. Pioneer 10 and 11 slow down, as if the universe itself is pulling them backward into the dark. The axis of evil aligns cosmic structure with our solar system in violation of the Copernican principle. SCP-06F6 exploded with the energy of 1 billion supernovae and left no trace in any known physics. Each anomaly stands alone in our catalogs, filed under different subdisciplines of astrophysics, explained away by different theoretical patches. But taken together, they suggest something far more unsettling than measurement, error, or incomplete data. They suggest that the universe operates according to principles we have not discovered, possibly cannot discover, possibly were never meant to discover. That the 95% of reality we call dark matter and dark energy might not be the invisible foundation of a cosmos we understand, but rather the visible edge of a cosmos we do not. That our models describe not the universe as it is, but the universe as it appears to observers trapped in 3 dimensions of space, 1 dimension of time, and the narrow electromagnetic spectrum of human perception. The signals continue. The anomalies multiply. The universe expands into configurations that should not exist, governed by forces that have no names, toward destinations our mathematics cannot map. We are not witnessing the birth of a new physics. We are witnessing the failure of physics itself to contain what we have built instruments sensitive enough to detect. The horror is not that the universe is stranger than we imagine. The horror is that it might be stranger than we can imagine.